Hello everyone, welcome back. This is lecture 9 of the lecture series Signals and System. In this video, we'll see about Fourier Transform. And first, to start with, we'll see the basic idea behind continuous time Fourier Transform. And then we'll see the derivation for Fourier Transform. And we'll see the convergence of Fourier Transform, just like we did for the Fourier series. And then we'll finally see the Fourier Transform for periodic signal. So Fourier Transform is nothing but it is the representation of aperiodic signals with complex exponential. So Fourier transform is a representation of aperiodic signals. Fourier series was periodic signals. So aperiodic signals by complex exponentials. So for Fourier series, it was a summation, and let us explore what happens in the case of aperiodic signals. So before we start about Fourier transform, let us review about the Fourier series. We have been seeing about Fourier series in the past 2 to 3 lectures, right? So if we have a signal x of t which is periodic with fundamental period t, then its fundamental frequency omega naught is given by 2 pi by t, and the signal itself can be given as the sum of complex exponentials, right? Ak is the Fourier series coefficient and e power jk omega naught t. Right? Now let us try to extend this for aperiodic signals. So we'll see the basic idea behind Fourier transform. So let us take any signal, any periodic signal x of t. So x of t, let's say it is periodic, it's having some structure, right? Is periodic and the time period is t here. So now let's say we want to construct a aperiodic signal which is just having one period of x of t, right? It's just having one period of x of t and it is 0 outside. So x bar of t is aperiodic and in one period alone it resembles x of t. Okay. So how do we get x tilde of t from x of t? So what if we take x of t and tend the time period to infinity? So what will happen? As t moves away, only this will be present. And if we move t to infinity, then we can say x of t and x tilde of t will be equal, right? So then x of t becomes x tilde of t, right? Can you imagine that? These copies just keep moving away and away from the original copy, right? And when t tending to infinity, they all will disappear. Only this one copy will be present, and that is what is x tilde of t. So x of t we can represent in the form of Fourier series, right? We have summation k equal to minus infinity to infinity ak e power jk omega naught t. So to find x of t in terms of complex exponentials, what we do is we tend t to infinity. So this is our basic idea. Okay. So we take a periodic signal which is resembling the aperiodic signal in one period, and then we tend the time period to infinity. Okay. So what happens to other variables, right, in the Fourier series? So this implies omega naught will tend to 0, right? And k, what will happen to k? K will remain same, but it will be, the number of terms in a given interval will increase, right? For example, if you take the representation versus omega or omega naught, so if you have k like this, 0, 1, 2, 3, 4, let's say it's omega, and let's say this is 1 omega naught, 2 omega naught, 3 omega, 4 omega naught. As omega naught becomes 10 to 0, what will happen to k? So k omega naught, what will happen? So they will be closely spaced, correct? Because omega naught itself is shrinking, right? So they will be closely spaced. So A case, if initially they were like at 0 and 1 omega naught, 2 omega naught, now after when we start to decrease omega naught, it will be at 0 and they come closer. So this we will visualize with an example, and we also need to know what happens to the summation. So we need to answer these two questions, right? Let's try to visualize it with an example. So we already know the Fourier series for this signal. We derived it in the previous class. It is nothing but the square pulse, right? Periodic square pulse. So how does it look? It starts from minus t1 to t1, x of t, and it repeats every t. So this is the graphical representation, and we already saw the Fourier series coefficient for this. We found out this one. It's nothing but sine of k omega naught t1 by pi k. We found it from this expression, right? 1 by t integral over t x of t e power minus jk omega naught t dt. So using this, we found out this. And this pi, how did we get? It was initially like 2 sine k omega naught t1 by k into omega naught t. So omega naught t was actually 2 pi. So this 2 cancels and we got pi. So let us take this representation since we have k omega naught together, and we can try to replace k omega naught with omega. So omega t1 by omega t, and AKs are nothing but sampling omega at k omega naught, right? So now if we try to get the expression for TAK, it is nothing but 2 sine of omega t1 by omega at omega equal to k omega naught. So how does this function look? 2 sine omega t1 by omega. So at 0 we need to take the limits, right? So let us take the limit. So limit omega tends to 0, 2 sine of omega t1 by omega. Why should we take the limit? Because both the numerator and denominator goes to 0 at omega equal to 0. Hence we need to take the limits. So we know sine x by x is going to be equal to 1, limit x tends to 0. So here x is omega t1. So I multiply and divide by omega t1. Okay. So this term will go to 1. So then I will be left with 2t1. So at omega equal to 0, this 2 sine omega t1 by omega is nothing but 2t1. And then sine it just oscillate, and by omega term it will actually reduce the amplitude of oscillation. So it will be something like this. And sine is an odd function and omega is also odd. So together they are even function, right? So they are symmetric about the x-axis, y-axis. So there will be something like this. Now to sample this, what I have to do? So I take this and I sample it at k omega naught, right? At omega equal to k omega naught for some value of omega, okay? So what will I take? If I take omega naught equal to 2 pi by t1, then this expression will be 2 sine k into 2 pi by 2 pi by t1, k into 2 pi by t1, right? So at 0 position will not change, but it will go to 0 at 2 pi k equal to n pi, right? Which is nothing but k is equal to n by 2 pi. So at every 0.5, right, pi cancels. So it is 0.5 omega naught, and this is 1 omega naught, 1.5 omega naught. It goes to 0. But our k itself is taking values like 0, 1, 2. So for 0 it will be this value, and 1 it is 0, and again 2 it will be 0, minus omega naught also it will be 0. Now if we take omega naught equal to pi by t1, then you will get 2 sine k pi by t1. Even here what happens? So if we just, so this omega naught will now become, like if I write in terms of t, it will not be nothing but pi by t1, 2 pi by t1, 3 pi by t1, and so on. This is again minus pi by t1. So for the previous value we had here, sorry, this sample is not there. We had this sample, and here also here we'll get the 2 pi by t1 sample, right? So these will be the AKs. For omega naught equal to pi by t1, what happens? It will be here 0, pi by t1, 2 pi by t1, 3 pi by t1, everywhere, right? Again here I made a mistake. This is minus pi by t1, and this is minus 2 pi by t1, this minus 3 pi by t1. So here you will have it here, right? So here, right? And what happens when you further shrink by 2? You will get at these midpoints, correct? You will get these as the AKs, right? And what happens when you keep on shrinking and finally tend to 0? And omega naught almost tend to 0, it will be very closely spaced, right? Infinitely small. So what did we observe? As we keep decreasing omega naught, the AKs, the Fourier series coefficient, become closely spaced, right? And as omega naught tends to 0, they become continuous, right? They are varying continuously, as you can see. Continuous, and they should represent the Fourier transform of the aperiodic signal. Why should they represent the Fourier transform of aperiodic signal? What happens when omega naught tends to 0? T is actually tending to infinity, which means this only one of this copy will be present. All this will be moved away, and x tilde of t will only have one square pulse. So that is an aperiodic signal, right? So that's Fourier transform can be got by tending omega naught to 0. And we observe this. So now using this concept, we'll try to derive it, actually using mathematical terms. Okay. So Fourier transform. So now let us redefine our quest. Okay. So now we have a aperiodic signal x of t. It is something like this. X of t is aperiodic. And it extends from some minus t1 to t2. Okay. Now let us build a periodic signal using x of t with some reasonable period t such that its structure is not lost. Because at least t should be greater than this signal length, signal width, right? Otherwise they will just overlap on each other. So that is what it means. Okay, so then how it will look like? We have this. Let's say this is x tilde of t is the periodic signal. So we'll have this minus t1 to t2. And we'll just have repeating copies at intervals of t, right? So now we have x tilde of t. For x tilde of t, we can find the Fourier series coefficients, right? And we can represent it in the Fourier series, which is nothing but summation over k, ak, e power jk omega naught t, right? And omega naught is equal to 2 pi by t. And ak's are nothing but 1 by t integral over t, right? X tilde of t e power minus jk omega naught t dt. Now I'll do simple manipulation here. So it can be over any period. So I take the first period, okay? So I'll take minus t by 2 to t by 2. So minus t by 2 will be somewhere here to t by 2. And x tilde of t e power minus jk omega naught t dt. But if you observe this signal and this signal, they are gonna be same in the region minus t by 2 to t by 2, right? So I can easily replace x tilde of t with x of t. So minus t by 2 to t by 2, x of t e power minus jk omega naught t dt. Okay. Now I want to remove the dependence of t in the integral. So what do? If you observe x of t again, it is anyway going to be 0, right, on both sides. So it won't matter if I just replace t with infinity, right? Minus infinity to infinity, anyway it will be 0. So what I will do is, I'll replace this t by 2, minus t by 2 to t by 2 with minus infinity to infinity. Why? Because x of t is anyway 0 in that case, it will not contribute. But since I want my integral to be independent of t, I am using this modification. So now I want to actually tend t to infinity. When tending t to infinity, what happens? My ak's become closer and closer, right? And my k omega naught becomes continuous. So I can say that ak into t will be a some constant, finite value, right? So why should t ak be finite? We already saw in the previous example, right? What did we plot here? It was actually t into ak. So we plotted t into ak and then we got this graph, right? So independent of tending t to infinity, even though we tended t to infinity here, this graph was not changing. Only the sampling points were getting closer and closer, but the shape of the graph was not changing. So it means tak will not change even if we tend t to infinity. That's what I mean by it is taking some finite value. Like it is defined. Okay. What happens to k omega naught? It becomes continuous. Right? Because we had k omega naught is nothing but the sampled values. right? The x-axis. And as omega naught tends to 0, it is going to be continuously varying. We can replace it with omega. So we can replace it with omega. So then what happens? I will actually call ak into t as some x of j omega. And this is nothing but the Fourier transform. This is called the Fourier transform of x of t. So now if I write x of j omega, what will I get? This is ak. So ak into t is x of j omega. And on the right hand side, I have minus infinity to infinity x of t e power minus j k omega naught becomes omega t dt. So it is similar to the Fourier series coefficient we found for Fourier series, but since it is continuously varying, we don't give the term coefficient and we just call it the Fourier transform. So now we can also write AKs in terms of x of j omega, right? It is nothing but for a periodic signal for x tilde of t. It is nothing but 1 by t x of j k omega naught, right? Simple. So this we got the Fourier transform. Now let us try to find x of t in terms of the Fourier transform. So we had this equation. Now if we tend both sides, limit t tends to infinity, x tilde of t equal to limit t tends to infinity, summation k equal to minus infinity to infinity ak e power jk omega naught t. So what is this right hand side telling? It is nothing but it is summing over the product of ak into e power jk omega naught t, right? Now let us try to represent ak in terms of x of jk omega naught. So it is nothing but limit t tends to infinity, summation k equal to minus infinity to infinity, 1 by t x of jk omega naught e power jk omega naught t. Since like these terms are in terms of omega naught, I'll write t also in terms of omega naught. And then I can actually replace this with omega naught tending to 0, right? So k equal to minus infinity to infinity. 1 by t will become 2 pi, omega naught by 2 pi, because t is 2 pi by omega naught, right? X of jk omega naught e power jk omega naught t. Now if I just 1 by 2 pi is constant, I take it outside, limit omega naught tends to 0, summation k equal to minus infinity to infinity, x of jk omega naught e power jk omega naught t into omega naught. So how is it like if I have this is omega, it is like of each is of with omega naught, it is like this, and this x of jk omega are like rectangles, right? And then I am taking the area under them. So if I shrink omega naught to 0, what happens? This becomes closely spaced and then I'll get a smooth curve, right? I'll get a smooth curve. So then what is the area? Area is nothing but the integral, right? Integral of this graph. What is this graph? This is x of j omega, because k omega naught becomes continuous. So I get x of j omega and e power j, again k omega naught becomes omega t. So the area will be nothing but integral from minus infinity to infinity x of j omega e power j omega t into d omega. This omega naught becomes infinitely small and it acts as the integrating constant. I mean the integrating variable. I'm really sorry. So now how will this equation look like? What will be the left hand side? It will be the x of t itself. So x of t is nothing but 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega t d omega. So this is our second equation. So our first equation was this. Right. So let us take this also there. Yes. Okay. So this is called as the Fourier Transform equation or relation. Since we are finding the x of j omega, which is the Fourier transform from the aperiodic signal x of t. And in this, what we are doing, we are representing x of t, which is a aperiodic signal, as an integral of weighted coefficients, like weighted complex exponentials, right? Which is continuously varying. Omega is continuously varying. In the periodic case, we had omega as harmonics, right? Harmonic relations of omega naught. But here it is like continuously varying. So then we have the integral instead of a summation. So this is called as the inverse Fourier transform equation, because we are inverting the Fourier transform back to x of t. So this is inverse Fourier transform equation. So what is our observation for periodic signal? We had harmonically related components of omega naught, right? Like omega naught plus minus omega naught to omega naught and so on, even 0. For aperiodic signal, what we have all real omega, right? And this x of j omega, like we call AK as spectrum of x of t in periodic case. In this case also, this is called as a spectrum of x of t. Why? Because it again denotes the frequency components. Frequency components being the c power j omega t, right? Components of x of t. So it is called as the spectrum. So once we call it a spectrum, we can have the magnitude spectrum, and the phase spectrum. So let us see an example. So example 1, we can take the signal x of t equal to e power minus at u of t. So exponentially decreasing signal, and we have a greater than 0. Otherwise, it will tend to infinity at t tends to infinity. We don't want such complications. So how will this x of t look like? To look like this. Now let's find the Fourier transform of x of t. So we have this equation, integral minus infinity to infinity x of t e power minus j omega t. So you should not forget the minus sign. This minus sign here and it is plus here. And dt. So u of t meaning it's only valid from 0 to infinity. So directly we can write 0 to infinity e power minus at e power minus j omega t dt. So this, since both are exponential and their product, we can combine them. So this is a plus j omega t dt. And taking the integral, we'll get minus a plus j omega t by minus of a plus j omega from 0 to infinity. Applying the limits, we get e power minus infinity minus of e power minus 0 by minus of a plus j omega. This will go to 0 and this will go to 1. So minus 1 by minus, we'll get 1 by a plus j omega. So my Fourier transform of x of t is 1 by a plus j omega for the exponential signal. And again, a is greater than 0 here. So now I can plot the magnitude and phase spectrum of this. So mod of x of j omega is nothing but 1 by square root of a square plus omega square, right? And how will it look like? So mod x of j omega. At omega equal to 0, it is 1 by root a. 1 by a, right? And as omega tends to infinity, this also goes to 0. So it goes to 0 like this. And what happens at omega equal to a? Say this a and minus a. They are symmetric, right? Because it is omega square. So at a, it becomes 1 by root 2a, right? 1 by a root 2. 1 by a root 2. So this is our magnitude spectrum. What this implies, it has the highest DC component, right, of 1 by a, and then other frequency components, the value's contribution to x of t is decreasing, and as omega tends to infinity, it also goes to 0. The contribution is going to 0. That's what it means. And let's see the phase of x of j omega. So this is nothing but, since they are in denominator, you will have minus tan inverse of a by omega. Omega by a. Because j sine by cos, right? So how do you plot this? X of j omega versus omega. What happens when omega tends to infinity? Tan inverse tends to pi by 2. But since there is a minus sign, you will actually have minus pi by 2. You will start from here. And then what happens? At omega equal to a, what happens? It becomes minus pi by 4. And at 0, it comes to 0. So it is tracing like this. And what happens at a, minus a? It goes to pi by 4. And when omega tends to minus infinity, it goes to pi by 2. This. So this is the graph, right, for the phase. Again, what it says, at 0, there is no phase difference, right? But as the frequency increases from 0, the phase is going negative. And as frequency decreases from 0, the phase is positive. Okay, now let us see another example. Example 2. We have x of t as the impulse function, the unit impulse function. Now let us see what happens. X of j omega, we have minus infinity to infinity x of t, and we recall that it should be minus j omega t dt. So this is nothing but the unit impulse, and we know the integral property of unit impulse. We just have to replace t with 0 here. So it will be minus 0, which is nothing but 1. So what it means, if we plot x of j omega, the spectral contribution, like each frequency contributes equally, right? And the amount it contributes is 1. So in the time domain, delta of t is this way, right? It is having 0 width and unit area but infinite height. So for that, in the frequency response, we actually see it is actually getting equal contribution from all the frequencies. So if you actually use the inverse Fourier transform, which is nothing but 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega t dt, right? Here it is plus. So now if you substitute, this is nothing but delta of t. So this will be e power j omega t dt. So this is a nice relation for the unit impulse, right? So it is just the integral of all the complex exponential from t varying from minus infinity to infinity. You will actually get this. And again, using Fourier series also you can represent. So ak you have 1 by t x of jk omega naught. Jk omega naught is again 1. So you have 1 by t, right? So it is like a Fourier, like the impulse train we call it. So 0, t, 2t, minus t and so on. It is something like this. Then what do you have? So that impulse train is nothing but summation k equal to minus infinity to infinity, the 1 by t, the time period, into e power jk omega naught t. Right? So 1 by t is constant. E power jk omega naught t. So this is called as the impulse train. So probably I'll put this in separately in a box so that you don't get confused. This is for periodic impulse train, we call it. Okay. So next let us look at the convergence of Fourier transform. This is similar to the Fourier series, not much to learn here. So what we have? So we have the aperiodic signal x of t, and then we find the Fourier transform. So which is nothing but x of j omega, and then we reconstruct x of t using inverse Fourier transform. So we get some x tilde of t is nothing but 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega t d omega, right? So for convergence, what we need? We want x tilde of t to represent x of t. Or in other words to say, if we have the energy difference between, right, the error signal E of t given by x tilde of t minus x of t. If you want, you can take this. And the energy in the error signal should be 0. That will give the optimal thing, right? We already derived it for the periodic counterpart. So we want E of t whole square equal to 0, which implies integral, but this is the energy will be integral dt, right? Integral dt minus n equal to 0, which means integral minus infinity mod x tilde of t minus x of t whole square dt should be equal to 0. So this is same as the periodic counterpart. So we leave it here, which means again it turns out Fourier transform is the optimal solution, right? So apart from this, we have the Dirichlet conditions. So it is also going to be same, because at the end we want this x of j omega to be finite, right? Which is nothing but minus infinity to infinity x of t e power minus j omega t dt. We want this integral to be valid. Should be valid. So for that we have these conditions. So first is x of t should be absolutely integrable. Why? Because this should be finite, which means the integral should be finite. And if you take the integral inside, you will find this goes to 1 and you just get integral minus infinity to infinity. Absolute value of x of t dt is equal to, should be finite, less than infinity. Right? Okay. And what is the second condition we had? X of t should have finite number of maxima and minima in any finite interval. So this is required for the integral to be valid. And third, we have the discontinuity. So x of t should have a finite number of discontinuities in any finite interval and each discontinuity should be finite. However, you can say the impulse is not finite, but since this integral is valid for the impulse response, like the impulse function, it still exists. The Fourier transform still exists. So these are like the sufficient conditions. So if you say if it is absolutely integrable and it is having finite number of maxima and minima and it has finite number of discontinuities and the discontinuities are finite, then we can say it definitely will have the Fourier transform. And there are also some exceptions like these impulse functions which may have the discontinuity of infinite value, but it still has a Fourier transform. And in case it is really useful to also describe the periodic functions, the Fourier transform of periodic functions, which we'll see next. So now let us look at the Fourier transform for periodic functions. Although the periodic functions are not absolutely integrable, right, from minus infinity to infinity, if we consider the impulse function to be valid, then we can represent these periodic Fourier transform of these periodic functions using impulse functions. Okay, we'll see how. So for any periodic function, we know it can have a Fourier series representation, which is given by ak e power jk omega naught t. So if I am able to find the Fourier transform of xk of t such that, like Fourier transform such that xk of t is e power jk omega naught t. Okay, so x of j omega gives xk of j omega gives this. Then like Fourier series, the Fourier transform is also linear. So my x of j omega will be given by summation k equal to minus infinity to infinity ak xk of j omega. Why? Because my x of t is nothing but summation k equal to minus infinity to infinity ak xk of t, right? And when I take the Fourier transform, all these are constant, ak's are constant. Only this xk gets transformed to xk of j omega. So now we want to find this xk of j omega that gives xk of t equal to e power jk omega naught t. So let us go ahead and find. So to start with, I need to consider the inverse Fourier transform, right? Which is 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega t d omega. So I want this to converge to something like e power jk omega naught t. So it is like replacing omega with k omega naught, right? So what I will do, I will take x of j omega equal to the delta function. So replacing means under the integral, we can use the delta function. So omega minus k omega naught. So this will give the 1 by 2 pi into e power j k omega naught t. I want to neglect this 2 pi also, so I add 2 pi before. So what will this x of j omega give me? 1 by 2 pi into integral minus infinity to infinity 2 pi delta of omega minus k omega naught e power j omega t d omega. So 2 pi cancels, so I'll get e power j omega is replaced with k omega naught t, right? Everything else goes away. So this is what I wanted to start with, xk of t, and I got it. So what is my x k of j omega actually? It is nothing but 2 pi delta of omega minus k omega naught. So we are using the impulse signal or impulse function. So then I can use this or this, right? So x of t periodic can be given as summation k equal to minus infinity to infinity ak e power j k omega naught t, and taking the Fourier transform, I get x of j omega, which is nothing but the Fourier transform of periodic x of t. This is also summation k equal to minus infinity to infinity ak 2 pi delta of omega minus k omega naught. There is no space here. I'll shift this. So 2 delta of omega minus k omega naught. So it is similar to finding the Fourier series. You just have to find AKs using this, right? Over one time period. X of t e power jk minus jk omega naught t dt, alright? And instead of writing e power jk omega naught t here, for the Fourier transform, you have to sum it over AKs and use this delta function. So how does it look on the graph? So x of j omega, omega we have equally spaced at k omega naught, 2 omega naught, 3 omega naught, and so on. And this side we have minus omega naught, minus 2 omega naught, and so on. And this will just be the impulse functions at these places. So this will be a naught, a1, a2, a3, a minus 1, a minus 2, and so on. So we get equally spaced impulses in the Fourier transform or the spectrum. So today we saw about Fourier transform, the convergence of Fourier transforms, and few examples on it. And also we saw the representation of periodic signals using Fourier transform. In the next lecture, we will see about the properties of Fourier transforms. So until then, stay tuned. Take care. Bye-bye.